Okay,
Okay,
so once again, hello everyone, and welcome to the last day of workshops. And today we're going to cover the Grover's algorithm. And at the beginning, I will talk about the classical, let's say classical game called in the notebooks inversion about the mean. And this will help us gain the intuition for how Grover's algorithm works. Then we will switch to one qubit representation. So we will take uh, our our state of many qubits to be represented as one qubit, and then apply operations to also see the intuition behind this algorithm and what it does. And at the end, we will get to the implementation. So what gates do we actually need to use in order to represent this game and the one qubit representation in the case of Grover's algorithm. So imagine we have a set of some numbers or variables, and each variable we start with each variable having each element having a value of 1. So we begin with the inversion about the mean game. So let's call, for example, we have elements like 0, 0. Let's maybe not, because this is like quantum. So let's think of some classical elements like 1, 2, 3, and 4. And now we know that we label the second element, and in the next step we flip the maybe here we flip the value of our second element. So instead of all now numbers having value 1, the second now has value -1. This is still 1, 2, 3, and 4. In the next step, we'll calculate the mean. So if we calculate the mean of, this is -1 here. If we calculate the mean, this will be, let's say that each element has the weight of 1. So we have the 1 minus 1 plus 1 plus 1 divided by 4, because we have 4 elements. And this is 3 over, no, this is actually half. So this is a half. So the mean will be somewhere here, right? Okay, so now we will flip the value of each element by the mean. So if we have here the value of 1, then the inversion about the mean will become 0, because we take the value of x and then subtract the distance from the mean. So mean minus x, right? Actually, x minus mean. And if we do that, then the value of the first element will be 0. And we can also verify this. We can also verify this expression here. So if the value of x is 1, 1, then -1, something not working here. We should get uh so this formula is actually not correct. But you can see that the distance from here to here is 0.5, and then we subtract this difference 0.5 from the mean. So this will be 0 here. And I draw this little graph so you can see that this works. So then this -1, the distance from here to here will be 1.5. So after the inversion from the mean, we should add this value to the mean. Oh, I'm sorry. We should add this value to the mean. And here I will write mean is equal to 1/2, which is this value here. And after that, we should see a element with the value of 2. This is the first element, second element, and the third element and the fourth element. They also have value 0. I draw them so you could actually see them, that they're there. Let's once again check the value of second element. This is indeed 1.5 plus a half, which is equal to 2. And in this one step, we have amplified the value of our second element, which is a marked element, to the greater value, and the others are 0. We can also imagine a game where you have a much larger set of those graphs. So instead of 1 to 4, you could have, for example, to 8. And this is a game you will be playing in the notebooks, and you will see what happens in each step to the marked element. You can also try the game with marking not only one element, but 2 elements, and see what will be the result of then flipping those 2 elements about the flipping the sign of those 2 elements, and then also calculate the mean, which will be somewhere here, let's say. These are our marked elements. We know that their value has been changed in each iteration. And then also calculate calculate the inversion about the mean. So after that, the value should be something like this of this first element. This is second, and this is eighth. And you will see how this game progresses in time. A very important thing to notice in those notebooks is that it's not always amplified. It's depending on how many steps you apply to this game, the value of the marked element can be amplified. But now, if I try to calculate the mean, once again, the mean in this case will be 2/4, which is 1.5. And then in the next iteration, you would see that 1/2, that the inversion about the mean will cause all the rest of the elements to go back to 1, because 0, this is the level 0.5 once again. So the distance from 0 to after the inversion about the mean will get transformed back to 1. And this the second element, which is our marked element, actually, we first have to perform, in the meantime, we have to perform the inversion. So I'll quickly do that. And then after the inversion, inversion of the negative sign of the second element. So this is once again 0, 0, 0, 0, 0, and this is -2. Now we calculate the mean. I'm sorry, that step was unnecessary. And then we can calculate the mean once again, which is -1.5. And then we apply a inversion once again. So inversion about this mean will become, the distance here is -1.5. So the inversion will transform this to value 1, and this will be transformed to this here is distance is 1.5. So we add 1.5 to this, and we'll get 1, value of 1. So we will get actually something like this. So it's not always the case that the amplitude of the second element will grow. After some iterations, it will fall, and you will also examine how this game progresses through time. I'm sorry, not here, only here. What is the formula used in the inversion about the mean? I do not remember exactly this formula, but I think that it is something like the value of x minus the value of uh, the value of x. No, from this we subtract the difference of this and mean. So actually it's mean minus x. So this is 2x, okay, 2x minus the mean. Okay, so this is the formula, and we can verify this by okay. This is It's really confusing sometimes.
Yeah, I think it should be mean times 2 minus x.
Mean times 2 minus, yes, exactly, right. Yeah, thank you. I'm sorry, Pablo.
It's fine.
Mean times 2 minus x. Exactly, thank you. Yeah. So let's now move on to the 1-qubit representation of this game. And in this case, we will consider elements such as first element, second element, third, fourth, fifth, sixth, seventh, and eighth. And each of this each of this element, we will consider a quantum state. And this will be a lot of writing here, but hopefully you will get the idea behind this. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so let's say now that our marked elements are, let's say, 3 and 4. 3, 4, and 7. Let's choose such states. I don't know if I can. Okay, and then we will try to construct a quantum state. But before that, I forgot to add a important note here that in order for this game to be more, let's say, quantum game, all of the values at the initial step uh, must must I mean the value squared must be equal to 1. So mm, so instead of writing 1 here, in case of the quantum gate, we will write the value of each element as square root of n, because uh, n is the number of the elements. And you can think of it as the probability amplitude of measuring each element. So you can verify this by writing the sum, and this must be equal to, I'm sorry, it should be 1 over n. This probability amplitude should be 1 over n. And you can verify this by summing the all n elements with the square root of n squared, because in quantum mechanics, the probability is described as amplitude squared. And this should give us 1, because this is a quantum state. So the probability of measuring all states must be equal to 1. From 0 to, you should start from 0, not from 1, from 0 to 7. I mean, it doesn't really matter. I mean, there are 8 elements, so indexing doesn't really change anything. But you also could do that. So this sum here is sum of n elements, which is 1 over n, which is then n times n, which is equal to 1. So now to prepare our game in the quantum regime, all of those of those elements have to have a probability of 1 over square root of n, because we have to preserve the length of this quantum state. Therefore, to achieve this, we can apply in our quantum circuit representation, right? 1, 2, actually we have 3 qubits. We can apply a Hadamard gate to each qubit. And after this operation, hopefully we should see that all of the amplitudes are the same and are 1 over square root of n. In this case, n is equal to 8. 1 over square root of 8, because we have 8 elements. But you could also write it as in terms of number of qubits. So in terms of the number of qubits, you would write this as 1 over square root of 2 to the n, when the smaller n is the number of qubits. Number of qubits. Let's see now what state do we get after applying all Hadamarts to each qubit. So we start with state 0, 0, 0. And after applying Hadamard gate to each state, we get a vector u, which is equal to uh, Hadamard of 0, tensor product Hadamard of 0, tensor product Hadamard applied to 0. And we can also write this as Hadamard to like power of 3, but this power is a tensor product here to simplify our writing, and this will help us. This notation will be helpful in later steps as 0, 0, 0. And now you can recall maybe from yesterday's lecture that applying Hadamard give us equal probability. So this vector u is going to be 1 over square root of 2 0 plus 1 over square root of 2 1 tensor square root of 2 1 tensor product, and I will copy this to save some time. Okay. Now we can expand those, multiply those tensor products and obtain a uh, uh, representation of those multiplied tensor products. So we will have 1 over square root of 8 because we multiply those square root of 2 3 times. And then the resultant vector should be 0, 0, 0 plus 1 over square root of 8, 0, 0, 1. And there's not any way to fast forward it. Here's 8, also 8. 1, 0, 1, 0, 0, 1, 0, yes. Plus 1 over square root of 8, 0, 1, 1. Plus, we have 4 states plus 1 over square root of 8. Maybe not. Maybe. Okay, let's leave it. Let's leave it as that. 1 over square root of 8. We have 0, 1, 1. Then 1, 0, 0. Plus 1 over square root of 8. 1, 0, 1. Plus 1 over square root of 8. 1, 1, 0. And the last term is 1 over square root of 8. 1, 1, 1. Now let's once again label our marked element, which is 0, 1, 0. Let's see, 0, 1, 0. 0, 1, 1. And 1, 1, 0. And now let's write it in a kind of different form. So now we will write them in the form of a vector. So in order to do so, I will group those three and write something like maybe also let's now call the sum of those elements a u y and the sum of the black elements as u x. So now I can write vector u as ux plus, this is x, plus uy. And then I will write 1 over square root of 8. And then I will take this huge vector as 1, 1, 0, 0, 1, 1, 0, 1, plus 1 over square root of 8, 0, 0, 1, 1, 0, 0, 1, 0. And these are the states from the top. You would write the states, this one here, or maybe in different ways, in different words. This one here corresponds to the 0, 0 state here. Again, one here corresponds to 0, 0, 1 state here. Next, the one state in this one in this column vector corresponds to our marked 0, 1, 0 element. And likewise, the next element is also marked. And by analogy, the next elements are not marked. Then we have a marked one and a not. But now we would like to write this as a qubit, as a bit 0, and this as bit 1. But now you can see that the amplitude don't match, because when we square those two amplitudes and add them, they do not add up to 1. So we have to somehow change how we write those vectors. So instead, I will write those vectors as, I will take, in this case, we have 1, 2, 3, 4, 5 elements. So take the square root of 5 from this to be 1 over square root of 5, 1 over square root of 5, 0, this is 5, 0, 0, 1 over 1 over square root of 5, 1 over square root of 5, and 0, 1 over square root of 5. This now vector gets really long, but I hope you get the idea. And here we have 3 elements, so I will take the square root of 3 in front of this bracket. And you can also verify that the coefficients here stay the same. So if I now would like to multiply all those vectors by, all this vector by a square root of 5, we will get back the original vector. So now I will do the same thing with the resultant, the second vector. So we have 0, 0, 1 over square root of now 3, 1 over square root of 3, 0, 0, 1 over square root of 3, and a 0. Okay, so now you can check that actually square root of 5 over 8, square root of 8 squared, plus square root of 3 over square root of 8 squared will give us 5 plus 3 over 8, which is equal to 1. So this is our proper quantum state. And now I will label this as unmarked vector. And this will be our marked vector. Okay, so let's now try to represent both vectors on a unit circle. And one important thing to notice is that when you will try to calculate the dot product between two vectors, the result would be 0, because 1 times 0 is 0, 0 times 0, 1 times 0 is 0. So in each element, when we sum up, the result will be 0, which means they're orthogonal to each other, which in turn means that we can write them on a unit circle as being perpendicular to each other. So we will draw a unit circle. Hopefully I will get this right. And now our marked vector will be here, unmarked. And our marked vector will be sitting here. So I will rewrite this. So let's rephrase our game with the inversion about the mean to a quantum game. So we begin with the state U, which is a superposition of marked and unmarked state. Then we switch the sign of the marked elements. So if the our qubit is U, which is marked plus unmarked, we will apply an operator, let's call it U, big UF. On a state U will become then minus marked and plus unmarked. So this operator acts only on the marked elements and change their phase and puts a minus sign. And as you can see from the unit circle, the resultant vector after applying the UF operator will just be a reflection about the unmarked vector. The unit circle is imperfect here, but this will be our state UF of U. Okay, so now now we have to do the inversion about the mean. And in this case, the inversion is simply the rotation about the U vector. So the resultant vector will be something like this. So let's call this inversion about the mean. And this is like, it's hard to define a mean in case of the quantum, this quantum superposition, but this game with the inversion about the mean is analogy to flipping the our state UF about this U operator, this U vector, which is our quantum state, our quantum superposition. So let's call this US, for example. Actually not. Let's call this okay, maybe US. Doesn't matter. So the US applied to, let's say, state this US gave us the state here, which we'll call like U prime, for example. So just call U prime. Now you can see that this here is much closer to the marked element vector. So now the amplitude of those the superposition changes. So it's no longer 5 over square root of 8 plus 3 over square root of 8. It's different, and the higher number will appear closer to the marked element. Therefore, by applying only two steps, we are able to measure the marked qubits with very high probability. There's a question from the uh, from the chat, and I will try to answer it. Maybe E equals 0.7, 1 squared root of 8. Okay, where B is a binary notation. Yeah, you can try to formulate this question differently in case of binary, but
Just wanted to propose a notation to save you from writing all those additions over and again.
yeah, okay, but I really wanted to do that because then I could mark the uh in the purple the elements that are actually marked and not marked, so you can better visually see the where the ones in this vector come from actually.
Sure, you got handy later. Thank you.
Okay, what does UF operator does? So UF operator uh, is it knows which elements are marked, and it applies a minus sign in front of those marked elements. When we will talk about the Grover's algorithm, I will try to formulate this problem a little bit different, but here's the intuition you might think of. So we will get to exact form of this UF operator in a second, but for now, you can think of it as applying the minus sign and actually making a reflection about the unmarked axis. Okay, do you have any questions so far? Maybe in the chat, because now I will try to go to the Grover's search algorithm itself. But one quick note before we start is that the number of iterations you need to do in order to get as close to the marked to the number of iterations you need to do so that the U vector gets as close to the marked element as much to the marked vector as possible is pi square root of n over 4, and this expression will also appear in the notebooks. And you can also talk about the complexity of a problem. So complexity tells you how many iterations, how many steps you need to perform in order to solve a particular problem in the worst case scenario. So in the worst case scenario, we need to apply pi over square root of n over 4 steps in order to get to the marked element as close. But it is also proportional to just square root of n. So sometimes those constants are just omitted. And we can also think about the mathematical representation of this inversion about the mean, this operator. So we said that the initial quantum state will be 1 over square root of n and 1 over square root of n number of times. And actually, the matrix representation of this US operator is actually, I'll change a little bit notation here if it's not too late, because in the notebooks it will appear as D. So I will here apply D because it will be consistent with the notation of the notebooks. So the matrix form of D is 2, 1 over n, 1 over n, 1 over n, and here also 1 over n, minus the identity matrix. And now I will try to prove to you that this matrix actually does what I say it does. So we can also represent this matrix here as in the bracket notation because it'll be much easier for us. And you may recall from the first lecture that this symbol is the same as 1 over square root of n, 1 over square root of n. And now we have a covector here. 1 over square root of n. And this operation will give us the matrix on the left here. Oh, I'm sorry. Okay. So let's write D as 2 times U minus the identity matrix. And as you may recall, the identity matrix is just ones on the diagonals and zeros on the off diagonals. So let's represent our quantum state now as the state A of U, any arbitrary state, plus B of U perpendicular. So we have vector U and some other vector that's perpendicular to it, and we can represent any vector on the plane as superposition of those two vectors. So we can say that we change our basis states. So they are no longer marked and unmarked, but the basis states are U and U perpendicular. So now let's calculate the effect of D on this our arbitrary state Q. And here I will show you also how powerful the bracket notation is. So we have 2 U minus 1 applied to A U plus B U perpendicular. Let's now expand our brackets, which is and then here comes also the amplitude A in front of the bracket, the first bracket, and the vector U plus B times 2 U and U perpendicular. And here's also the identity matrix. So we have to remember about it. So 1A minus AU minus BU. Right? Okay. So now we have from the orthonormality of those vectors, we know that this should reduce to 1 because this is the length of the vector. And now you can treat this as first calculating the inner product, and then the result will give us the vector U. Instead of calculating the matrix first and then U. So that's why the bracket notation is very powerful and very convenient, because it applies, it is very simple to apply a matrix in the orthonormal basis, because now we can see that this expression here gives us 1. And likewise, this expression here gives us 0, because those two vectors are once again perpendicular to each other, which means their scalar product is 0. And you can choose the order, you can choose the order in which you apply the operation, but you cannot choose the order in which you place those vectors. This is very important, important note. So this reduces to 1, this reduces to 0. So in the end, we have 2a u minus a of u minus b, which minus b u perpendicular. And this simplifies to a u minus b u perpendicular. So from this, you can see that we got from state with a plus sign here, and we got a state with a minus sign in here. So once again, the state is the reflection. The state here is, after applying this d operator, is the reflection about the u vector. So once again, let's recall it. The form of D matrix. This is here, or we can also say that D is equal to that D is equal to 2u, u, and minus the identity matrix. Do you have any questions so far to this? I don't see any. Okay, so let's now move on to implementation of Grover's algorithm. So in our game, we assumed that we know which elements are marked. We assumed that we know that this second element was marked, and we assumed also that these elements are marked. But in Grover's algorithm, we assume that this UF, this operator that changes the face of the marked elements, has very complex form. So we actually don't know this. This is called an oracle. So we give a query to the oracle, and the oracle will give us some value. So we may think of also the function f of x as oracle, and if the input of this function is, for example, 0, 0, this function will output f of x will output 0, 0, 0, and the last element will be 1. Let's assume we have such a function, but we don't know what is this function. So we actually don't know this this table, but we assume for the sake of the simplicity and for understanding that we know it. So in the classical, let's review the classical example. In the classical example, you will have to calculate the value of evaluate the function 4 times to find a value. Once again, let me rephrase it. In the classical terms, in the worst case scenario, you'll have to apply the function 4 times, like I'm applying here, 4 times in order to find a correct value. Okay, so it took me 4 queries to execute the function, and now I can see that this outputted 1. So it's not that simple that we just rewrite the table. We actually don't know this in, let's say, real world scenario. And in classical computing, once again, this took me 4 steps. And in general, it will took n times for n elements in the worst case scenario. So we can also say that the complexity with this big O in classical terms is n. But in the Grover's algorithm, we, based on the this quantum game and the number of iterations we had to do to this game, we can say that I'm looking for the nodes here. We can say that this is square root of n. And I'm looking here for the formula. Oh, here's the formula. Okay, so in quantum, we will try to show you that this is using this game. We'll have one over square root of n iterations. So there are two different implementations you can see. The first, I will write the gate representation of the first implementation. So we start by applying, and let's for simplicity assume 2 qubits, so 4 elements. We first apply Hadamard gates in order to prepare our game and have a equal probability of obtaining each state, such as here. Then we apply this operator, and in this case, in this particular case, it will be Control Z operator, but we'll call this is our oracle UF. So we don't know actually in real world example what this does, but for the sake of this example, we assume this is Control Z gate. Next, we will have a Hadamard gate, a Z gate, and another Control Z gate, and Hadamard afterwards. And I'll try to show you that this is our operator D. The same as written here. And then we can read our results and see what happens. But actually, this is not how the Grover algorithm is implemented in the notebooks. The Grover algorithm in the notebooks is implemented quite differently. So this is one way of writing this operator D, but in the notebooks, we will use the auxiliary qubit, and this auxiliary qubit will perform the Control Z gate through the phase kickback algorithm we talked about yesterday. So you can remember the phase kickback, and here should be the plus state as we recalled from yesterday. So we will get use of this phase kickback phenomenon to implement a Control Z gate here. Okay, so let me begin with Hadamards. And we apply our oracle UF. And this will take some qubit, we don't know which state, and flip its sign. So let me try to now rewrite and guess, try to see what this, and here we also have a operator X and X and Hadamard for our auxiliary qubit. And let's see what effect does the operator UF have on two different bits. like x and y. And based on our table, you can prove that this operator has a property that it transforms our state to the to the state here, and this is the binary addition. So we can rewrite all this expression here. So 0, 0 gets transformed to 0, and f of x is 0, so it is 0. 0 0, 1 is transformed to also 0, 1. But actually, no. I'm sorry for a second. Zero. Okay. So 1, 0 will be transformed to also 0, 0, 1, 0, and 1, 1 will be transformed to, this is still 1, but now we have 1 and the output of f of x is 1, so we will have 0 here because this is binary operation. I think so. If I'm not mistaken. So let's now examine how this operator, when applied to this unitary operator, when applied to x and minus state, what will be the effect of it? So we will start with the x and a superposition of 0 minus 1. I'm sorry, I have to admit some people to Zoom still. And then we will get 1 over square root of 2 UF, then 0 minus UF x and 1. So here I am just rewriting these expressions in front of the bracket. So now I can say that 1 over square root of 2 of x. And now this operator applied to 0 will have df. I'm sorry, I missed the x here. So applied to this state will give us state x, 0 plus f of x. This is long continuous calculations, but hopefully we will manage to do it. And also x. Now this unitary operator applied to this state will give us minus x and f of x, binary addition to 1. And now we will rewrite our, get rid of this summation here. So we would have just x 1 over square root of 2 f of x minus f of x, binary addition to 1 state. And then here comes the trick. So now we will write this in different form. So we will write minus 1 to the f of x. 1 over square root of 2 and superposition of 0 minus 1. And then why this is so? So if x, if our f of x is, if the result of our f of x is 0, then we will have 0 minus 1, and this, if f of x is 0, this will reduce to 1. So this state will be the same. But if the f of x is 1, so now it is 1, this state will become 1, and this state, 1 plus 1 in binary, is 0. So this is 0, and now you see that the 0 comes with the negative sign, so that's why we have a minus 1 in front of that. So you can see that the oracle, this oracle UF, applies a phase shift to the state of the x qubit only if uh, the result of the f of x is 1. So in this case, the actually the x can have value 0, 0, and these are our two qubits, and this minus state will be our auxiliary qubit that will help us in our calculations to help us apply this unitary operator. Do you have any questions to this? I think this is really complicated, and it's really hard for myself to deal with this algorithm. But if you have any questions, it will be more easier for me to create a concise story of this. I don't see any. Okay, I'll try to move on. Next, we would like to show that well, so we would like to write this this unitary operator as our gates. So in this example, we know that in general we don't know the form of this oracle, but for the sake of the experiment, once again, we will try to formulate a physical gate. So in order to do this, we can see that this oracle, based on the function f of x, transform state 0, 0 to state 0, 0, the state 0, 1 to 0, 1, state 1, 0 to 1, 0, and state 1, 1 to minus 1, 1. Because the minus, the 1, 1, the f of 1, 1 has the value of 1 in our example, so therefore we have to put the minus sign in front of our state after applying this UF gate. So you may recall from the yesterday's lecture, in case of the multiple control constructions, and in the notebooks you were asked to construct different kinds of gates, and now we will have the implementation of such a gate. And as I said before, this can be implemented using the control Z gate, I'm sorry, control Z gate. But in the case of the notebooks, this will be implemented as applying the phase kickback algorithm. So we will then have, maybe I'll write this in this circuit form. So we apply our phase kickback algorithm. So only if both qubits are in state 1, 1, then this controlled NOT gate will have the effect, and the effect of this control NOT gate will be the phase kickback of both those qubits, right? So both those qubits will get a minus sign in front of them. So there are two ways of actually implementing this gate. This can be either a control Z gate or phase kickback algorithm. Good. So we now know how to implement this UF gate. And now let's try to see how our D gate could be implemented. And once again, I will recall that the D gate has the form of two U's minus the identity matrix. And now we'll try to write it in the different form. Now, remember that our state U is the Hadamard. We apply the Hadamard n times because we have n qubits. Hadamard applied n times to the 0 operator. So therefore, I will write 2 Hadamard to the like tensor power or something like this to the n 0. And if I want to do the bra of this, I just need to reverse the order. So I have now Hadamard apply n times after, and also minus the identity matrix. Now we can also write the identity matrix as Hadamard gate applied n times, and another gate Hadamard gate applied to n qubits. And this is a fact from the first lecture when we applied two Hadamard gates to a sequence of qubits, and it didn't have any effect on them. So let's rewrite this as 2 n 0 0 Hadamard n minus Hadamard n, like this. Okay, so now we will try to factor out these Hadamard gates and write Hadamard gates n. This is 2 0 0 minus minus 1 and another Hadamard gate at the end. Is it clear? I hope so. If not, then you can ask questions on the chat. And unmute your microphone if needed also. So excuse me for a second. Okay, I'm sorry, I'm back. Okay, so let's now try to, we know that we have to put some Hadamards at the beginning and some Hadamards at the end in order to apply this D, which is the inversion about the mean gate. And but what happens with this gate here? This is the question. So let us look at the effect of this gate at any state. So we'll apply this gate, this 2 minus 1 on any arbitrary state, for example, x. Therefore, we would get 2, 0, 0, x minus x. Now, if there are now two possibilities. If x is 0, and by 0, I mean a vector 0, so I'll try to make it bold. So a vector 0 is actually a 1 in front at the beginning, and no matter how many zeros there, how many elements, this is a vector of a form like this. And this is important because we can have any number of generalized qubits, not only 2. So this is what I mean by the vector 0. And since 0 is with 0 is 1, so this will become 1, then the effect of our gate will be 2. Maybe write it more cleaner way. So the effect of our gate on state 0 will be 2, 0, 0, 0, minus 0, and this is 1. So this will be state 0. But if x is somewhere different than 0, so it'd be any state where this here is 0 and any state where you have 1 here or 1 here, doesn't matter, somewhere in between, then we have by the orthogonality and orthonormality of the states, we have that this, actually I'll get this notation here. This is 0 minus the state x. So therefore we will get minus x. So you can see that this quite similarly to the UF operator, this also changes the sign of x if it's not 0. And the question is how to do it. So we can also use our function, our unitary operator UG, and construct an function such that f of g of x is equal to 0 if x is equal to 0, and g of x will be equal to 1 if x is somewhere different than 1. And you can think of this gate as the same gate like in case of our auxiliary qubit. So UG applied to x should have the same effect as minus g as the gate we talked about before, right? This is very similar to example to previous one. But now our function g of x is different. And we also have this auxiliary qubit. But the question is how to now implement this UG in the in sense of the quantum gates we know. So the Hadamard and operator. So actually we will try to construct and consider a different function, the opposite function, which the value of x will be equal to 1 if x is equal to 0. And this function will return a 0 if x is different than 0. So this function has an exactly opposite effect to this g function. G prime function has opposite effect to the g function. But right now, so to think of this step here, you can apply and first this u g prime and then apply an x gate in order to get this UG function. But actually, I think I missed something here. Yeah, okay, it's fine. So actually, you can implement this function here with also with the based on the knowledge from the multiple control constructions. And you can do so by implementing the gates such as x. Let's get this here. And this is our Q0, Q1, and this auxiliary qubit. And we set its value to minus state. So here we have the minus state. So you have to apply an x and a Hadamard. And here we apply x gates and a control NOT gate. So from the multiple control notebooks from yesterday, you can call that this has exactly implements the function here. So if all of the qubits are 0, right? So if all qubits are 0, the output of the function will be 1. So here we have changed we'll change the state. But if either one of these qubits is not 0 or both of them are not 0, then here will not have any effect and the auxiliary qubit will not be changed. But in order to now take a switch from G prime to G, we'll have to apply another excess gate after each and every qubit. Okay, so now we have the form of our UF. I'm sorry, our UG, and this will be our UG prime. There are a lot of gates, but finally, I think we can come to the final conclusion and write that our algorithm will take the following form. The Grover algorithm in its pure form as in the notebooks. So once again, we start by forming a superposition of all of the qubits. So here apply Hadamard and also Hadamard. Here we prepare our auxiliary qubit in the form of X gate and followed by Hadamard gate. So this is the initiation step. Then we apply our oracle operator which is in the form of a controlled NOT gate. And maybe I will try to draw it differently. So here we have the preparation phase, prep. Here we apply our oracle UF. And for the simplicity of, once again, in normal conditions, you would not see, you would not know the what gate it is. But for our case, we know that this is double control Z gate. Then we implement our D operator, which is the inversion about the mean. And for this, we apply two Haramarts at the beginning, as shown here. Then we apply our to our operator, this operator here, which we derived to be this UG. So this follows by an X operator, an X gate, followed by a control NOT. And we need to revert our state for it to have the form of our D operator. So actually this here is our UG, and this whole part here is our, I'm sorry, I also forgot about the Hadamard gates at the end. So at the end, we apply another set of Hadamard gates. And this is our whole D operator. And at the end, we can measure our results. And hopefully, in this particular example, with this particular oracle, the result of the measurement should be 1 and 1, because this is how we defined our function to work. And in this 2-qubit case, you are able to measure 1 with 100% probability. But in general, with the higher number of qubits, you may not be able to match the marked state exactly, but maybe you will get very close to it. And the idea behind Grover's algorithm is that you can amplify the state quite quickly to the marked state. And in general, in this case, we applied those two operators only once. But in general, you would need to repeat those steps square root of n times. So repeat, square root of n times for it to be as close to the marked state as possible. Do you have any questions? There are a lot of calculations, a lot of gates. I hope you didn't get lost. If you did get lost at any step, please tell me and I will try to go through it. Are you sharing your notes on Discord? I will share them after the lecture. Yes, I will share all of those notes after the lecture. And thank you for reminding me about it. When? Just after the lecture. So in like 5 minutes. On Discord, yes, on Discord. I will post them on Discord. No problem. Are there more questions? I mean, you can write also on the chat, like, did you understand the basic idea behind this algorithm? Will you be able, would you know an application of Grover's algorithm? Right now, it's very vague to find an application, but there are some applications. I heard that some guys use this algorithm to compute some finance problems. but that's really too advanced for me. But an application of a Grover search could be to find a database, to find an item in the unsorted database. And for this, you would need only square root of n times to find the item in the database instead of n. But actually, what's very interesting is that what you can call the first quantum computer, let's say, actually implement the Grover algorithm. So the two researchers, or three of them, took the molecule of chloroform, and the molecule of chloroform has a form of carbon and hydrogen and three chlorine atoms. Three chlorine atoms, and is like the trapezium, kind of. And they put this molecule in an external magnetic field. And now you can consider the spin of the hydrogen atom and the spin of the carbon atom. They can be either aligned with the magnetic field, which will be our computational zero, or they can be anti-aligned with the magnetic field, which we will call our computational one. And it's very interesting because using the NMR machine, which stands for nuclear magnetic resonance, they were able to apply different magnetic pulses to the molecules. And instead of taking the one molecule, they took a bunch of them. So actually very large number of molecules were implementing the Grover search algorithm. And they were using the NMR machine. They were able, with pulses of different durations and length of different strength, they were able to implement all of those gates and all of this strategy here to compute a Grover's algorithm. But here you need in this particular example you need 3 qubits. So the researchers actually took our different form of the Grover's algorithm, which is this form, and here you can only see that you only need 2 qubits, and therefore they were able to perform those gates, measure the states, and verify that they were correct. So it's actually the demonstration of the, let's say, first quantum computer, but it's not really practical in any ways, I think. So to answer your question, the application of algorithms may be in the databases, search of the database, or search for the quantum database, for example. Yeah. Any other questions? Since we are in the last days of the course, give us some advice that you think will be useful to us in this field. I think linear algebra, and once again, linear algebra. If you understand mathematics, for example, for a very long time, I was really not able to understand how those brackets work. I was so stuck with this, but once I understand fully once I took the course of linear algebra at the university, I really understood what's going on here. So I suggest that you took a really strong to really understand quantum computing. I suggest you take the really good course on linear algebra, because quantum theory is actually a linear theory. Is Yeah, that's my suggestion. And please upload these recordings to YouTube as well. I would like to view these lectures again whenever I need to revise. That is the question to Pavel, but I could try to convince him to post those lectures once again. So yeah, we will consider it. Thank you. You need to take free calculus before you take linear algebra in USA. Okay, I understand. In my case, it was not the case. I took the linear algebra 1 and linear algebra at the same time as calculus 1. But I understand you might need some more time in different countries, but I really suggest a strong foundation in linear algebra because I think this is absolutely necessary to understand the mathematics behind quantum computing. Okay, I understand. I see your comment. Do you have any more questions, more comments?
It would be nice if
Yes,
you
exactly.
put the lecture on the Discord, you know?
This recording of today's?
Yes, yes.
Yes, that Pavel will do maybe in 1 hour or two.
Okay.
But all the other recordings are, I think they're available.
Mhm.
I saw them and you need to just enter the password to view them.
Thank you.
Thank you, Richard, for your comment. I really appreciate it too. Yeah, I hope you gained some knowledge. And thank you for all the questions, because the questions are really what make you think about, I mean, transferring knowledge to other people. What is the password? The password is available on the Discord server. Hopefully I meet you once in Poland. I hope to meet you too. uh, how are you going to help on the labs from today on? Yeah, I will try to with the labs. I mean, I will also be available till 9 o'clock in Poland, so 1.5 hours. But if you have any questions later, you can also write them on Discord and I will try to answer them, but maybe not immediately, but after some time. Yeah, thank you for your comments. I really appreciate it. So, yeah, thank you very much. It really means a lot to me. So, if you don't have any more questions, I would like to once again thank you very much for those 5 days of lectures. And I hope to see you on Q Nickel, which QPoland is also organizing. And yeah, goodbye.